4.3.1 Simple harmonic motion, bouncing spring problem. A weight attached to the end of a long spring is bouncing up and down. As it bounces, its distance from the floor varies sinusoidally with time. You start a stopwatch. When the stopwatch reads 0.3 seconds, the weight first reaches a high point at 60 centimeters above the floor. The next low point, 40 centimeters above the floor, occurs at 1.8 seconds. We want to first sketch a graph of this, and then we're going to write an equation. So in order to sketch the graph, of course, we need to know what our maximum is, which we just said 60 centimeters above the floor. Our minimum at our low point, it said, was 40 centimeters. And the reason we need those two, because it helps us find our amplitude and our midline. So amplitude, remember, is the maximum minus the minimum divided by 2. So in this case, we would have 60 minus 40 divided by 2. So our amplitude ends up being 10. Then, of course, the midline is your maximum plus your minimum divided by 2. So 60 plus 40 divided by 2, which ends up giving us 50. And for this, if I start to make a sketch of this, so we have 60 at our max, our midline's at 50, and then 40. And on my graph, I know at 0.3 seconds, we have a maximum at 60, and at the next low point at 1.8 seconds, we have 40 centimeters off the floor. And we know, again, our midline's here. So I know somewhere in between I have to hit that midline. So I know my graph starts up here and then starts to come down. So you can see that, remember, from a max to min is only half of a wavelength. So if I want to figure out that distance of half a wavelength, I can just subtract 1.8 minus 0.3. So 1.8 minus 0.3 gives me 1.5. That's half a wave. So the full wave, of course, would be the period, which would be adding this 1.5 plus 1.5, or 1.5 times 2. So when we do that, we get a period of 3 seconds. So if the period's 3 seconds, then we know our key points are going to go by 3 divided by 4, your period divided by 4 equal parts, which is 0.75. And so we can use that 0.75 to add it to that 0.3 to get our next key point. Of course, you could always take the average, add these together, and divide by 2 to figure out what this key point is. It works just using it that way as well. So if I have 0.3 plus 0.75, I get 1.05. To get the next midline key point, I would add another 0.75 to 1.8, which gives me 2.55. And adding another 0.75 to that would give me 3.3. So you can even check when you are finished graphing, you can see the distance from here to here would be 3.3 minus 0.3, which gives us our period of 3 seconds, which is equal to 1 wave. So now that I can see that, I can go ahead and write the equation for this. So remember, for my equation, I can use a sine or cosine. It looks like cosine's probably easier, so I'm going to do y is equal to a times the cosine of b times x minus c plus d. So we have our a and our d. It looks like a phase shift would be moving to the right 0.3, or if I use cosine, I could do to the right 1.8 if I use a negative in front for the amplitude. So for this, I'm going to do the positive value. I'm going to start up here, and I need to figure out my b value then. So remember that the frequency times the period is equal to 2 pi. So b is equal to 2 pi divided by your period, which in this case is 2 pi divided by 3. So now my equation is going to be y is equal to the amplitude, which is 10, times the cosine of 2 pi over 3 times x minus 0.3 plus my vertical shift, which is 50. So that's the answer to B. Then for the next part, it says we want to predict the distance from the floor when the stopwatch reads 17.2 seconds. So we can use our calculator for that. Remember, when you are using your calculator, make sure your mode is in radian mode, which mine is. So then in my y equals, I plugged in 10 cosine 2 pi divided by 3, x minus 0.3, and plus 50. So if I go to my table, I can just do that and scroll down to 17. So you can do it that way if you want. Remember, you can also go to second window table set and you can plug 17 into the table start and then look at it that way. So I get 40.86 for 17, but we want 17.2, so I need to fix that. So I can actually type in 17.2. That'll be a little easier. So 43.31 would be the centimeters above the floor. Of course, I could also graph this. If I'm graphing this, remember you want to change your windows. This is from a different graph that I did. So I would do my x minimum as 0, my x maximum, we had 3.3. Oops. And then for my y minimum, I'll do 0. Oh, actually, let's do 35 to 65. So here's my graph. And of course, I can always do second and trace and do the value in 17.2. So that's another way you can do this. For that, oops, I'm not looking at 17.2, so I need to go all the way to, let's do 18, because I forget, if you don't have it on your graph, then your calculator can't find it. So using the table probably was easier here. But like I said, we can still use our value. Just need to make sure our graph shows up to 17. So second trace value, 17.2, and then I get 43.03. So that's just another way you can find that value. So if we go back here, the next answer for C would be at t equals 17.2 seconds. I know that my y is equal to 43.31 centimeters. And then for the next part, for D, it says, what was the distance from the floor when you started the stopwatch? So of course, when we start the stopwatch, that's at time is equal to 0. So on my calculator, I can just go to my graph table, or I can go to second trace value, 0, enter, and I get 58.09. So y is equal to 58.09 centimeters.